Have you ever wondered why some neural networks learn slower than others? The answer might lie in something called the saturation problem. Today, we'll break it down mathematically, see why it happens, and understand which activation functions can overcome it. Activation functions determine the output of neurons in a neural network, but some functions, like sigmoid and Tanh, have a major drawback: they saturate. Saturation here means that for every large or very small inputs, the output flattens and the gradient becomes almost zero. Let's see this mathematically. The sigmoid activation function outputs value between 0 and 1. But when x becomes very large or very small, the gradient or the derivative of this function approaches 0. If we calculate the derivative of fx, when x tends to infinity, fx will go to 1 while the derivative of fx will be 0. Similarly, when x tends to minus infinity, fx will be 0 and the derivative of fx will be also 0. This small gradient slows down learning in gradient descent, making it harder for the network to improve. Similarly, the Tanh outputs value between -1 and 1. It also saturates because of its derivative. When x tends to 0, Tanh x equals to 1 and its derivative is equal to 0. Similarly, for x tends to minus infinity, Tanh x tends to -1 and its derivative tends to 0. This again leads to slower learning. When gradients become too small, the model struggles to update its weights during backpropagation. This is called the vanishing gradient problem, and it's a major obstacle in training deep neural networks. The network may take too long to converge or fail to train effectively. ReLU, or the rectified linear unit, avoids saturation for positive inputs. Its derivative is simple. The derivative of fx is equal to 1 when x is greater than or equal to 0 and is 0 otherwise. For x is greater than 0, the gradient is 1, meaning that it doesn't vanish. For x is less than 0, the gradient is 0, so the neuron doesn't update. This simplicity allows faster training and avoids the saturation problem entirely for positive values. As you can see, ReLU avoids the small gradients that slow down learning in sigmoid and Tanh, making it the better choice for most modern neural networks. For a practical demonstration, I've trained a simple neural network on MNIST handwritten digit dataset with 2 hidden layers using sigmoid and ReLU activations separately. If you analyze the loss curve, you see that the ReLU loss is quite low and it is converged quite faster than the sigmoid loss. And that's how activation functions like ReLU solve the saturation problem, speeding up training and improving performance. If you found this video helpful, don't forget to like, share and subscribe for more machine learning insights. I'll see you in the next video.